Oh. I think it's happy now, Frank, on YouTube. Annoyingly. Yeah, that's right. It should be YouTube/user/Chuck Empire. One, two. Yep, mic's working. Cool. All right. And what am I going to do? Disconnect. I'm just going to be working out which of these things I should leave. Probably that meeting. I'll join back in with you guys in a second. Sorry, just give me a second. I'll get my my streaming setup working. Okay. Well, hey, what? All my my cameras are confused now as well. Oh boy, I just can't seem to get this right today. Okay, I think I'm now finally starting to be in a good situation with streaming. I'm sorry about those delays and difficulties. Let's make sure that I'm connected to you folks on Zoom. I'm going to copy that link and join a meeting. No, not make a new meeting. So at least I can see what's going on over here, and if Frank yells at me and says, if I see him waving, then I'll know I have to stop. Cool, all right. Folks, thank you for bearing with while we get my very silly computer system working. You know, the reality of online teaching is that sometimes everything is just a ridiculous mess. So luckily, it's 11 o'clock at night for me, so I've got a beverage to enjoy while lecturing to you about machine learning. You folks can't start on beverages until after this session. Now, where were we up to? We just trained a neural network. Oh, it's not working. There's a bad thing happening. I'll turn my volume up again. It's not working. There's a bad thing happening. Yes. I'll turn my volume up again. It's not working. There's a bad thing happening. Yes. I'll turn my volume up again. It's not working. Oh, maybe I should mute myself. Why'd you chat to me? Is it working now? I did forget to mute myself. Okay, it is working now. I've got an all clear from Benedicta, so I'm going to continue with the lecture in some ways possible. Maybe we'll end up going a little past 4 o'clock for you folks, but no, I think it was my fault. Again, everything is my fault today. I take full responsibility. I'm just a crazy Australian all the way down here in the middle of the night streaming to you folks. So where were we? We're in these recurrent networks. We had created one to generate some text, and we did so. And I think so far at this point, what I showed you was how to build a recurrent network with this kind of layer-based programming method. And I used this thing called an LSTM. So I guess what I'm going to talk about for the next 15 minutes or so is what is LSTM, what does that mean, and why is it interesting? So the crucial thing is that the RNN that I've told you about so far, this simplistic RNN, doesn't actually work very well. And there's a very good reason for that. I'm not going to talk about bidirectional RNN. Oh, these are other architectures of RNNs. I'm going to skip those for now. The main, the crucial thing here, I'm not going to skip them for now, I'm going to go back. We can take this basic idea of having a number of neurons and sending information between time steps can be modified in different ways, make more complex, more simple arrangements. And there's there's three which I think are very important. The first one is this idea of a bidirectional RNN. So if you've got a sequence, so far we've just been kind of taking information from the past and moving it into the future to help us do. I just made myself small for a minute. I realized I was looking at my slides and I wasn't small yet. Take information in the past to help us make future predictions. And sometimes that makes most sense, right? If we're trying to predict what the weather is tomorrow, we are not going to use today's weather to predict the weather in last month. We only want to use the past going into the future. But there are some instances where it is useful to sort of look both ways down a sequence, both up and down a sequence, to make a good prediction about something. And you can use a bidirectional RNN to do that. The intuitive idea is that you just, instead of having one RNN, you have one set of inputs that goes two ways to two different RNNs. One is going leftwards and the other one's going rightwards, like these little arrows down here, rightwards and leftwards. And then we combine the information from both RNN steps to make a good prediction. Another interesting RNN would be one that is going to look at a whole sequence, and instead of make one prediction, then we're going to take its state to then unwind and create another sequence. So it's called an encoder-decoder or sequence-to-sequence architecture. So just the same as we had our previous RNN, we're going to call this one the encoder, and we're not using its outputs to make any predictions. We're just using it to generate an RNN state, which we then copy into this decoder network, which will then make our predictions. And the decoder network gets started with some kind of starter information, which is not really an input, just a starting token. This one, a good example of a sequence-to-sequence problem, by the way, is something like translation. So if you have a sentence in Norwegian and we want to translate it into English, we might use an RNN to scan the whole sentence in Norwegian, translate that into an English sentence, and then use it by using a decoder, which will then take some state, some low-dimensional transformation of the meaning of the sentence in any language, and use that then to prime a decoding RNN to spell it out for us in English. And then deep RNNs, and this is one which is like easy and useful in this kind of Keras layer-based building of deep learning networks framework, because we're just going to take one RNN and then take its output and put that into another RNN. So each of these RNNs now forms a layer of our deep RNN network. And as it turns out, adding a few layers to one RNN does tend to make it work better. It's very popular. People did this a lot. Intuitively, you might get some kind of hierarchical knowledge when you have multiple layers of a neural network, but that's sort of up for grabs, that idea, whether that is actually true or not. And a typical setup is not to have too many layers. Like, you know, that if you have these big image recognition CNNs, they might have like 90 layers or something, tens of layers. An RNN is typically with like 3 recurrent layers. They're still like a very deep network because they're deep in kind of the time dimension, not the hierarchical dimension. So we were talking about the reasons that a simplistic RNN might not work. And the reason it might not work is that every time we have a step in our RNN, going back to our earliest RNN diagrams, the unrolled one, every time we add a step, we are essentially taking some state here and multiplying it by v. It's just gone 11:30 here and my lights have turned off automatically. I'll just turn them back on. Hello lights, thank you. Okay, I knew that would happen. So we've got our h, and we're going to transform it using this matrix V, and then get another value called ht, or add that in as an input to this network. We then get ht, transform that with V. Now, essentially, we're sort of multiplying. It's matrix multiplication each time, right? ht minus 1, v ht minus, or regular t. So we're multiplying by something like the same matrix each time. And, you know, if you take something all the way back here, suppose we have an h0, and you multiply it by v, and then that number kind of goes into this network. A bunch of stuff happens to it, but maybe there's some remnant of that number still occurring, and then we multiply it by v again. Okay, and we keep multiplying by v. And intuitively, if you multiply by the same number over and over again, it's multiplying by a matrix, but intuitively, if it was a number, if that number was more than 1, then it would kind of end up being very large, the number we're getting. And if it was less than 1, if we're multiplying by that number over and over again, whatever this multiplier will be will end up being taking our result to 0. So this is the intuition behind this idea that the things that you're multiplying, that if you're multiplying the same matrix here over and over again to this hidden state, then it will end up either exploding or vanishing, going to 0. And in practice, it turns out that vanishing is the problem. So it's called I've made a very hand-wavy version of this, but it's called the vanishing gradient problem. And I've got a slightly less hand-wavy explanation of it over here, where we've got if each ht depends on multiplying by a matrix by ht minus 1, then eventually we've got ht equals wt, the matrix to the power of t, times h0. Of course, we're multiplying matrices together, so you know there's a lot of pluses and multiplications going on there. But if you're a devotee of vector calculus, you might remember this thing called eigen decomposition, where you can take this eigenvalue or diagonal matrix, sorry. Yeah, that's the eigenvalue, sorry, it's a vector, lambda, and put that kind of decompose this matrix W into a particular kind of matrix Q with this vector, and then another matrix Q, the transpose of it. And then eventually you can end up with this vector being multiplied by itself over and over again, and any particular number in that vector or that diagonal matrix, which has the eigenvalues of W, will be multiplied by itself over and over again, and if they're less than 1, of course, that will go to 0. So some information might be lost, is what I'm trying to say. And there are There is I guess, a hierarchy of less and less hand-wavy versions of this argument, but I'll leave that to the reader to look at it in more detail. Anyway, it turns out that this is a big problem, and it really caused RNNs not to work for many years. And the solution, as it turns out, was this idea that instead of using the same matrix every time for V, we're going to put in here a little tap, which is going to kind of turn values on or turn them off. I like the idea of it as a tap because you kind of turn taps on and off. Usually it's called a gate, so we're gating these RNNs, letting some values in and keeping some out. And these little gates can change the hidden state a little bit at each step. And the cool thing about these gates, or the interesting thing, is that the taps are not set in any one position. They change at each step, and they're changed by the values of the RNN at that stage. So the RNN actually learns to turn the tap on and off, to throw away some values and keep some. So these gates are controlled by learnable weights as well. This means that the intuition is that we then get a path through time to previous information all the way down back through our RNN. Hopefully we get a path through time with derivatives that don't explode or vanish, and that means we can do backpropagation through time. All of our algorithms work well, and our system will be able to learn from information far away in the past. Now, the most popular of these gated RNN designs was this thing called the long short-term memory unit, which actually has 3 gates, not 1 gate. So it's got 3 gates. It's kind of a charismatic name, I guess. Long short-term memory. Why is it called long short-term memory? The idea is that because of these gates, it lets it choose whether it's going to store information far away in the past or override it with information that it's just heard. So I think that's where this long short-term thing is coming in. So inside a long short-term memory unit, it's now a little bit more complicated than just Wx plus B, or even Wx plus Vx, Vht minus 1 plus B. We've now got a couple of different transformations, a hyperbolic tan function there, some other matrix multiplications for each of these gates. It's going to have its own set of weights. An input gate, forget gate, output gate. So the input gate is controlling how much of the information from the input. This is kind of the normal flow of information through to the predictions. The input gate controls whether that is open or closed, the input side. I'm going to put myself on the left for a minute, sorry, so you can see this diagram properly. Oh no, I'm not too bad. We've got an output gate which is controlling whether our predictions are actually being exported to the output of the LSTM unit. Before that, or the copy of that is stored as our regular state, and then we end up with another state which is just kept inside the LSTM each time, this self loop. So this is kind of its internal memory state. And there's another gate which is called the forget gate, because it allows the LSTM to clear its memory. So if this forget gate is changed to 0, we're multiplying something by 0, we're multiplying the previous information it could remember by 0 so that it can start again fresh. So there's some old LSTM papers by the originator was this guy called Jürgen Schmidhuber, a very charismatic person as well, and fairly wild ideas over many years, wild and interesting, and he called it learning to forget, and said that was an interesting concept for machine learning, which as it turned out it was, so it's very useful. So that is the long short-term memory unit. And now you've seen inside one, you know what we're talking about when we say LSTM. There are other gating units as well. There's a simpler one called, for instance, this gated recurrent unit. For the moment, LSTMs, I guess, are winning in terms of practical use, but also I think, although I still think RNNs and LSTMs are really beautiful machine learning ideas, Many people have moved on to different kinds of sequence learning models that use more like convolutional neural networks. There's this model called the transformer, which has kind of taken over a bit. Shed a tear for the LSTM, no longer as useful. One cool thing you can do with LSTMs is use this memory state, or see what's going on in this memory state and see if it corresponds to anything useful. So there was a researcher called Andrei Karpathy who did a lot of work in LSTMs about 5 years ago, around 2015, and he had this idea of visualizing what was going on in these LSTM units, and found out that when he was doing making some of these character RNNs, character level RNNs, he could track the LSTM cell state and find that there was one cell which was responsible for knowing where you are in the line. So it would slowly go, its value would get higher as you got towards the end of the line. And then he found another one which would turn on when the neural network was inside some quotes. So it would remember, it would be keeping the memory that we're still inside a quote, and you would need to turn off at the end when the next quote mark occurs. We're going to look at another interesting RNN example in a minute. I don't want to leave you with just the text one, but there are lots of things you can do with RNNs, and this is where it starts to get fun, to find some data, find a data set, find something you care about, and start to apply RNNs to it and see if you can get something cool to happen. There's a researcher called Bob Sturm who had an RNN project called the Folk RNN. He was interested in Irish and Scottish folk music, and he took this library of folk music in this kind of ABC format, just text format, and used that to train a character RNN, and then came up with these different folk RNN predictions. And one cool thing about his model is because it was just learning the text, it would actually name the system. This one was called Bornity Horse, which is a kind of cute name. It does seem like it would be a kind of jig, I suppose. You can do other things. There's lots of exciting projects that people do of different kinds of levels of coolness. Someone's got a blog called AI Weirdness, which I think is just excellent. And she has made up a bunch of interesting things. In particular, this sequence of new paint colors invented by a neural network was quite hilarious. Like, it would just take again, it was a character RNN, it would just make up a name and then generate a color. So some of these make sense, some of them don't. Dorkwood kind of looks like that. That doesn't really look like a flower. Sandsdan, that kind of looks sandy, and Turdley seems self-explanatory. So that's the neural network's embedded colors embedded by a neural network. Something I've been interested in for several years is generating music with RNNs. There's an ongoing project by a group called Magenta at Google, a little team of researchers working on musical problems. They have a lot of state-of-the-art in music generating RNNs, but what I'm actually going to show you is, I'm going to skip the rest of this and then I'll move on to another talk. I'll show you a very bad musical RNN that generates music from the Legend of Zelda video games. So here's one of my Jupyter notebooks from my my website. You can find this down here somewhere, continuing musical sequences. The idea is that we can take, I'll just load the first thing, we can take a sequence of notes, and similarly to letters where we gave each letter a number, we can apply a number to each musical note and then turn that into a sequence of numbers and then turn it into a sequence of one-hot encodings, etc., and get some results by applying it to an RNN, training it to predict the next note, putting that note in again at the back of the sequence, and then continuing forward. So you may know this if you're interested in music technology, but we have this system called MIDI for applying numbers to different notes on a keyboard. If you have a computer keyboard and you press one key down, that will just send a number over a serial connection to your computer. In particular, if you play middle C on that keyboard, it will send the number 60. That's the only one I know. And then I can work out all the other numbers. I know that every time I go up one half step, that's a single number. Up a whole tone is 2 numbers. So the MIDI standard has 7 bits, so it's 127 different notes, numbered 0 to 127. And then we can encode some rhythm within our system by using some extra numbers to let us know whether our note should continue or stop. So this is a very simple music representation, just to turn music into a string of numbers. I'm actually going to be limited to doing 16th notes or semiquavers in the bar. So if I have a 4/4 bar, I'll have 16 different steps through time. Every 4 will be 1 quarter note, and every 2 will be 1/8 note, and every 8 will be 1 half note. And I'm going to use these extra numbers, 128, to be like stop whatever note is playing. So that's like turn the note off. And then note number 129, is going to be do nothing. So if I had this little melody, do, 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 it would be 69 for that note A, then 3 129s to do nothing, then another 69 to turn on that note, a couple of 129s, 69, 69, a couple more 129s, then 66 there, and then 3 more 129s, and then this sort of implied note turn off now, 128 at the end. So I've got a big script here which can extract these numbers from MIDI files, and the MIDI files I'm interested in this particular little demo are songs from The Legend of Zelda. I can prove to you that my little system is working because I can take this little melody, do 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 do, which is a famous Australian folk tune called Waltzing Matilda, and turn that into a sequence of numbers, 69, 129, 129, 129, 69, 129, 129, etc. And then turn it back, and I get broadly the same thing in this, using these Python libraries. Now I have already set up my data set, and I can now slice it up, just like I sliced up those Star Trek episode titles into different examples. I can do some stats on my different examples, and I can tell now that most of my numbers are kind of in the center of the piano keyboard, and there's not too many that are very high and not too many that are very low, and then there's a lot of 128s and 129s. They're all over my data set. And now I'm going to define a new RNN, and this one is going to be a multi-layer RNN. This one actually will have 2 layers of LSTM units, and then 1 dense layer, which will transform the outputs of the LSTM units back into the kind of right shape of data to turn back into MIDI notes. So we always need to have this kind of end layer for transforming back to our representation format. I'm going to open that one. And what I really want to show you with this one is how we can adjust the sampling of an RNN. So I've already done the training. I'm not going to train that in front of you. It takes hours to train this one. So it's got a lot more data and it's a lot bigger. But I can do this sampling procedure. So what I want to do is change my probability, or take the probability distribution from my model at each prediction step. So it's not predicting a certain note. It's predicting a probability of which note on the piano to hit, or do nothing, or turn the note off. So I can take that probability distribution and modify it a little bit, either by kind of smoothing out the probabilities so that probabilities that are less likely before are now a bit more likely, and some probabilities that were more likely before are now a bit less likely. I can also make it more pointy, so the ones that are more likely are now way more likely, and the ones that were less likely are like 0. So I can emphasize the likely ones or de-emphasize the likely ones. And it's often called changing the temperature of a probability distribution when we do that. And all we need to do to get that to happen is multiply the numbers inside the softmax function. So this is my softmax function is in here somewhere. There's some exps for all the little e's, and then dividing by the temperature is adjusting those prediction values. So I've got those functions organized, and now we're going to make some music. I'm going to use a temperature of 1.0, which would kind of be the standard predictions straight out of my model. I've started on one single note. I'm not using 30 notes to start with this time. And now I've got some Zeldic kind of music. Now this model is actually really overfitted. So you guys can tell me what the output is like. I'm just going to make sure I will get the sound here. I think I'm going to get the desktop audio when I play it. I just want to check that it really will work. Nope. Oh, I see it's muted. Whoops. I will unmute it and then turn it up. Fade it in. Here we go. Wow. So that sounds pretty Zeldic to me. It sounds like one of those dungeon melodies. Now, what I might do, should I turn it down or turn the temperature up? Down will make it more boring, up will make it more interesting. Everyone always says up, so I'm going to choose that. 2.0, how about that? So we're asking the neural network to make more outlandish choices. Maybe 2.0 was too far to start. I'll try 1.5, see if we can get something which is a little wilder, but not quite as wild as all that. So this one now, it's not getting stuck on the same idea because the RNN is getting kind of kicked out of an idea by a outlandish prediction, perhaps. Let's try 2.0 for temperature. So we're making it choose ever more unlikely predictions. And maybe we'll keep going 5. This is where we get to like the kind of music high school and kind of stuff. Stockhausen will be proud. And if we keep going even further, I guess we start getting just random numbers. Yeah, so this was my Zeldic musical RNN. I'm going to show you one more kind of example or little idea and then give another demo of that before we go today. So I'm going to potentially eat a little bit into Farzan's time. Sorry, Farzan. As I promised Frank that I would do it. Mixed density RNNs. So far we've talked about RNNs which are generating predicting one of a set of options as the output. So making a kind of 1 of k prediction, 1 of 10 items, 1 of 127 keys, 1 of 26 letters, 1 of 2 buckets, 1 of 10 colors, whatever. It's one discrete decision from a collection. But we don't always want to make those kind of predictions. Sometimes we want to make predictions from all continuous values, right? Any number between 0 and infinity and minus infinity, including all the ones in between the integers. So of course we can do that. We could just cut off the softmax function from the end of our RNN, and we would have a real valued output. But it turns out that if you just remove that, it's not quite as easy to train your RNN or any neural network to do what you want it to do. And that's what I'm going to talk about today, a kind of solution to making systems like RNNs so that they can make useful, continuous, valued outputs and still be kind of expressive and creative like the RNNs that we were just looking at. We were easily able to take the same output from that RNN and tune the probability distribution to make more creative or weird predictions or more conservative ones. So that's what I want to do with our for continuous values as well. So the solution here is these mixed density networks. The reason why I like doing this is that there is lots of continuous data which is very interesting in the world. Things like gestural data on a screen, or moving little knobs, or playing a wind instrument or playing a violin. The pressure of the bow, the pressure of all your fingers are all really meaningful to the music you get out. So we would want to model that data as well. The difference here, is that we're looking at two kinds of probability outputs from a neural network. The output of a neural network is usually considered to be some kind of probability distribution, or or it could be seen that way. So for discrete data, we can use this kind of categorical distribution, just a list of numbers that add up to 1. For continuous data, we get weird kind of lumpy or one big lump normal distribution, or multiple lump multimodal distributions. So these ones are a lot harder to deal with in statistics. So unfortunately, things get a little bit more hairy. So the typical kind of continuous distribution is this normal distribution, the Gaussian distribution, the standard probability distribution we use for everything. This has got two parameters, right? The mean, the center, and the standard deviation, which is this width. Standard deviation, and this is the mean. And then there's this pretty complicated function. This is the function to define this curve here. The probability density function is something like this plot here. So it tells you the probability of, if you had some phenomena modeled by this distribution, the probability of ending up with a number here would be the height of the curve at that point. So that's the probability at that point. So unfortunately, normal distributions don't always fit your data, right? Data can be complicated. It's easy to fit a model to any data. You just calculate the mean and the standard deviation. Anyone can do that. You add all the numbers together and divide by the number of numbers you had. And then the standard deviation is a few more calculations after that. So we can, if we have a data set that looks like this histogram, we can calculate a normal distribution that looks like that, but it doesn't fit it very well at all. So there are other kinds of distributions that you can use to model this more carefully, more closely. So the one that I'm talking about right now is this thing called a mixture distribution. So we're actually going to take several normal distributions and add them together. Each normal distribution will have a different mean and a different standard deviation. And then we're also going to get a value which will be the height of those. So each of these will have a different height. And my goal now is to make neural networks that are going to output this mixture distribution so that I can use it for stuff. So this solves our problem. In this case, I happen to know the right parameters for my mixture distribution, but usually we have to learn them somehow. So neural networks can be used to model complicated data, but usually the usual approach to taking a linear activation function at the end of your neural network for your predictions, and then training with the mean squared error, or just the distance between your output and the target data. The problem there is that this is equivalent to fitting a normal model. So if your data doesn't fit that model very well, then you're kind of stuck. There's details in this paper by Christopher Bishop. You can go and have a look at that. On the other hand, we could use our neural network to simply take a lot of outputs that are going to be the parameters of our mixture network, a bunch of different means, a bunch of different sigmas or standard deviations, and a bunch of different heights or pi, and we will use that to create a mixture density model instead. So now we can have a network that models complicated distributions. Woohoo! Easy, right? I will show you a little example in Keras. I'm not going to run this one. I just want to show you the output. But if we've got it's not that hard to find difficult data. If you've got a bit of data like this, where the input is the x-axis and the output's the y-axis there, this is sort of an inverse sine function, so twisted a little bit. If we wanted to model that function with a neural network, and we used a standard neural network, a normal kind of feed-forward mean squared error loss function neural network, we would get a prediction like this for it, because it's trying to take the average of these different kind of points here. If you have -5 as the input, it wants to take the average of all of these, and it gets a prediction somewhere like there. So it looks like it's training very well, but it's performing very poorly. If we use a mixture density network, on the other hand, we can get a much better result. The only problem is that we then need to design a loss function which is going to work. The mean squared error function is very simple. You just sort of square each number, square the errors and take the mean of them. Not very much work there. Getting the loss of a mixture density network means you have to figure out what the probability density function is for that mixture distribution, which is tricky. It's a more complicated function. I won't go into the details, but luckily in TensorFlow, again, there are some good abstractions to help with this. And then we can get a network which gets a much better result. It is able to sample from this richer kind of probability distribution and get a different output each time. So even though we're taking the same input, -5, we can sample stochastically from this distribution and get lots of different options. Much, much better. Now I'm going to show you a demo of how one works for a pretty cool problem. So this one is a Chinese character generation network. So this is a cool idea. I didn't originate with this idea. It came from a researcher called David Ha, who has a lot of really interesting and creative neural network demonstrations and ideas on his blog. But he took a kanji data set with all these Chinese characters in it and used it to train a mixture density network. And the cool thing here is that this system it's not taking a picture of each kanji, it's taking like the pen movements on a tablet for them. So we're predicting not the pixels on a picture, but the next motion of a pen in 2D space. So this 2D movement across space and whether the pen is down or up. So I've got my system loaded. I did a bit of work a few years ago to write a mixture density network library for Keras so that we could do demos like this, which anyone is welcome to use in their projects if they're interested in this kind of stuff. I wonder if I have that data set already. I'll just download it again in case. So it's now loaded 10,000 kanji from this data set, and we can have a look at one. Here's what one looks like. It's got a big list of pen positions and numbers that are either 0 or 1, And the 0 means the pen is down on paper, and the 1 means the pen is up. So that's much, much easier, or very useful to recognize that. I'm going to try plotting this example. And unfortunately, the plot doesn't look very good, because actually what's stored in this data set is all the diffs of each pen movement. So it's the difference between moving it over here. So that doesn't look good. If we do a cumulative sum on that, example.t0.cumulative sum, we will get a training example that makes sense, one character. I didn't cope with the pen up, but the pen should be up in that movement. So now I'm going to make my MDN RNN. I'm going to use 2 RNN layers, and the output at each step of my network will not be a discrete probability distribution. It'll be a mixture density network, or a mixture density model, a mixture distribution of 3 normal distributions, 3 dimensions. One will be for the X dimension, the X movement, one will be the Y movement, and one will be whether the pen is up or down. So that's what I've got here. There's my 2 LSTM layers. And then there's my MDN layer, which replaces the kind of output layer that I had in my music example and Star Trek example. Okay, same idea as before. I'm going to process this data and turn it into inputs and outputs, but I'm not going to train it today. I've already trained it, I hope. I think I downloaded that one already. I'm just going to load it up into the same kind of network, 2 layer LSTMs and 1 MDN layer. This one's bigger now. You can see I've really moved up in the world from my first Star Trek network, which only had 100,000 parameters. Having 2 LSTMs, 2 LSTM layers means that all of the connections have to be interconnected. That means a lot more weights, and I've also made them a bit bigger. And now I've got almost 1 million parameters, but still tiny by like cutting edge standards. I really only deal with tiny neural networks, I guess, at the moment. And similarly, I've got some functions here to do the drawing and do our sampling. Similarly, I've got a temperature measurement here. And the temperature, what happens when I've got one of these neural networks, let's see if I can find a bit of data here. No. When I sample from it, I can't just, like with my categorical networks, I could just choose which of my blocks I should choose. Maybe this one's highest, I'll choose that one. Oh, well, even though it's highest, I'm just going to randomly choose this one instead if it's a low probability. When we're dealing with a mixture model, the first thing I want to do is to sample from, choose which of the normal models I'll sample from, and that's essentially a categorical choice with 3 choices, right? So this one's the highest, that's the most likely to be chosen. This one's the lowest, least likely to be chosen. So that's going to be the same kind of choice as before, and I can still use this softmax temperature adjustment to make that choice. And then I'll sample from one of these normal models. For instance, this one would have some width here, and obviously I'm likely to choose something near the mean by a stochastic procedure to sample from a normal model, but I might be more likely to choose from something further away from the mean, and I can actually adjust the standard deviation to make this wider, because if this is wider and flatter, I'm more likely to choose numbers that are further away from the mean. The narrower it gets, the closer to the mean I'm likely to choose. So that's 2 adjustments I can make now, not just one. I can make a adjustment for which normal model to sample from, and an adjustment for how wide that normal model will be. So that's why I've got 2 temperatures. One's for the standard deviation, and one is for choosing between the multiple normal models. So this little demo, now I can actually draw these kanji that I'm generating. That one doesn't look that good. I might choose a low temperature there and maybe make it a bit longer. There we go. Now we've got some more action. So if I make this temperature very small, it tends to do the same kind of stroke over and over, or never kind of rarely leave those strokes. And if I make them big, oops, my light went out, ran out of battery. If I make them big, it tends to make smaller strokes and never kind of complete a character. It just sort of keeps moving down the page. And also, my model will never stop. It just keeps drawing forever and ever and ever. I can make this 500 and it will just sort of keep drawing away down the page until it ends. Well, I'm well over time now, and I think I didn't really have too much else to say. I guess sometimes it's hard to think of applications for this kind of neural network, but there are lots of things that have two-dimensional continuous variables. Example, robot positions, locations or sensor data might have multi-dimensional continuous data, biosensors for predicting the state of a human being in some situation. Maybe the output would be multi-dimensional continuous data. There's lots of things that could be used for. So I hope that these two lectures have been useful for you. I think that you're about to start on this journey of getting deeply into one particular project that you choose, but also hopefully along the way you gain a bit of context for how lots of different ways that machine learning is used and how we actually do research to push this cutting edge further. So I'm just going to hand it back to Frank now, and he can perhaps yell at me if I'm you gain a bit of context doing something weird, so just avoid getting feedback there. How's it going, Frank? You'll have to chat to me so I know what you're on about. Or I'll plug my headphones back in or something. Where are they? Ooh, these headphones. Okay, here we are. Oh, thanks everybody. A little clap. Ute. Thank you all for joining me. I'm back on this one.